In this video, we're going to look at the components and the properties of a numerical solution. So I'm going to walk through the numerical solution procedure, an overall framework that we can use to kind of visualize the process by which we take a real problem and get a numerical solution. And then we're going to look at some properties of numerical solutions that are either necessary or desirable. So first of all, the numerical solution procedure. So there are 3 steps in the procedure, and they take us from the physical system, which is reality, to the numerical solution that we get in the end. And the 3 steps are as follows. The first step is to apply the appropriate physical laws and models that take the real system, the reality that we're trying to model, to represent, and turn that into a mathematical formulation. So we get a mathematical model that gives us the governing equations, normally in the form of ordinary or more likely partial differential equations that govern the physics of the system. And then the second step is to discretize that continuous mathematical model, the PDEs or ODEs, to form a system of linear algebraic equations, a big matrix problem, which we then solve in step 3 to get the numerical solution. So let's just walk through that in a little bit more detail. So the first step, physical laws. So this is things like conservation of mass, momentum, and energy, physical laws that we know apply to the particular scenario. And then any models, these could be idealizations, they could be approximations, anything that we're going to introduce that simplifies the problem. We might assume, for example, that something behaves according to the ideal gas equation of state. Or maybe in a fluid mechanics contest, we'll assume that the flow behaves in an incompressible fashion, or maybe an inviscid fashion, so there's no friction. So there's all kinds of assumptions, approximations, simplifications, idealizations that we make in addition to the application of the physical laws that govern that particular scenario. So that's the first step. And this is typically what is done in our engineering science and engineering analysis courses. And then, if possible, you get the analytical solution. Now we know from our experience in those classes that those analytical solutions are often quite limited. In the area of fluid mechanics, for example, there are very few analytical solutions, closed form solutions of the Navier-Stokes equations. They only apply for very simple geometries, very simple scenarios. But if you can, you get the analytical solution. If you can't, then you proceed with the second step of the numerical solution procedure. And that second step is the heart of the numerical method, and that is the discretization. There are different ways to do the discretization. It could be using a finite difference method, finite element method, finite volume method, spectral method. There's different discretization approaches. And along with that, we're going to have a grid or a mesh that indicates the resolution on which we're going to get the approximate solution. But the whole point is to turn our continuous differential equations by discretizing them to get a system of linear algebraic equations. We love systems of linear algebraic equations because they're just big matrix problems and we know how to solve them. Various matrix solver techniques that we can use to get the numerical solution. Now keep in mind, these are not the AU equals B matrix problems that we had in part 1. These could be many, many thousands or even millions of unknowns that we need to solve for. So let me just talk about those steps in a little bit more detail. We've discussed the first step, application of physical laws and the models and idealizations and so forth. But let's look at the second step, the discretization, in a little bit more detail. So again, we're going to approximate the continuous differential equation or equations to form a system of linear algebraic equations. The unknowns that we're looking for, the solutions that we're solving for, are going to be the dependent variables at the grid points. So here's the idea. So we have, say, a 2-dimensional XY problem. And we have a rectangular domain where we're going to solve for u of xy. That's the dependent variable u in terms of the independent variables x and y. That's the continuous problem. What we're going to do is discretize this. So we'll have the same x, y domain, rectangular say. But now we're going to discretize this into a grid or a mesh, depending on what you want to call it. This is why it's called discretization. We take our continuous domain and break it up into little discrete elements, little discrete pieces. Then each of the intersections of these grid lines, those are the discrete locations in space, in this case, or space and time more generally, at which we are going to get the approximate solution. So rather than getting the solution at every x and y in the domain, we're only going to get the approximations of the solution at each of these grid points within the domain. And then the system of linear algebraic equations is going to be solved for those values of the dependent variables at the grid lines. And then the third step in the numerical solution procedure is to get the solution to that big linear system of algebraic equations. There are various ways to do that. There are direct methods and iterative methods. Direct methods are things like Gauss elimination or taking the inverse of a matrix A so that U is equal to the inverse of A times B and so on. These are the methods that we discussed in Chapter 1 for solving systems of linear algebraic equations. Iterative methods are step-by-step procedures that when you do them over and over again, you iterate over and over again, you get closer and closer and closer to the actual solution of the linear system of algebraic equations. We'll talk about both of these methods, why you might want to use one or the other. The key here is to remember that we're solving enormous systems of linear algebraic equations, and direct methods like Gauss elimination, LU decomposition, and so on often do not scale well to very large systems. And so iterative methods tend to scale better, but there is a price that has to be paid for that. The method of discretization, so whether we used finite difference methods, finite element methods, that is going to produce typically a certain structure, some sort of structure to the matrix problem. Sometimes the matrix problem might be sparse, meaning lots of zero coefficients. Maybe it's structured, maybe it's unstructured, tridiagonal, but the properties of that matrix problem will be determined by how we did the discretization itself. Now, each of these three steps in the numerical solution procedure produce their own set of errors. So step 1 produces modeling errors, step 2 produces discretization errors, and step 3 can produce iterative convergence errors if we use an iterative technique. Let me say at the outset, generally these cannot be quantified numerically, but we need some sense of the contribution of each of these errors to the final solution. So the modeling errors, that is the difference between the actual flow, so that's the reality at the very top, and the exact solution of the mathematical model. That's the governing equations that result after step 1. The difference between those two, those are the modeling errors. Those are the errors that are introduced because of the modeling decisions that we made in getting the governing equations. Then the second step, we get discretization errors, and there's two contributions there. This is the difference between the exact solution of the governing equations and the exact solution of the algebraic equations. Now again, we don't have either. If we had the exact solution of the mathematical model, we wouldn't need to get the numerical solution at all. So we don't have these, but conceptually that's what it represents. And again, there's two contributions. There's the method by which we did the discretization, and that has an inherent error. So if I use finite difference methods and say they're second order, so second order would mean that the order of the truncation error, which is this part of this discretization error, is order delta x squared, the distance between adjacent grid points squared. So the smaller the delta x is, you square it, it gets even smaller. So the method of discretization leads to an inherent error, truncation error, in the numerical solution. We're also going to choose a computational grid with a particular resolution on which we're going to get the solution. This can be refined. That's a choice that we make, how many grid points, where we put them, how much resolution we provide. But obviously, the better resolved it is, the more unknowns we have, and the larger system of linear algebraic equations is necessary to solve, and it'll take longer to do so. So there's those two contributions to the discretization error. And we'll be talking a lot about these because our focus in these videos is going to be on the second and third steps. The first step you did in another class. That's how you got the governing equations that we're now trying to solve numerically. And so we're going to focus on these steps 2 and 3. Now the iterative convergence errors, again, that depends on how we solve the system of equations. Do we use a direct method, in which case there's no iteration and there's no iterative convergence errors? Or did we use an iterative method, in which case there are? And the reason why you would have iterative convergence errors is as you do the iteration over and over again, the error is going to come down, come down, come down. Eventually it's going to start leveling off. And at some point you'll decide it's not worth continuing the iteration anymore. The additional computational time required to do more iterations is not worth the small gain you get So you say it's converged and you stop the iterative process. So that introduces iterative convergence errors. That's the difference between the iterative numerical solution and the exact solution to the algebraic equations. Now, you can see very clearly where this pragmatism in that Dawes quote from an earlier video now comes in. At every step of the numerical solution procedure, we're making decisions that impact on these errors. If my sole purpose is to eliminate these errors, I'm going to end up with a huge problem that might not be practical to solve on the computer resources that I have. So I have to make pragmatic, practical decisions at each step, 1, 2, and 3, to get a manageable process that I can solve in a reasonable period of time on my computer and get a solution that serves my purposes. So there's a lot of pragmatism, there's a lot of practical engineering judgments that need to be made along the way. So now let's talk about the properties that we seek in our numerical solutions. These are things that need to be true in order for us to have confidence that the numerical solutions, which are approximate, represent reasonably well the solution for the system that we're considering. The first one is consistency. I'm not going to say a lot about consistency in future videos because this is something that's inherent to the method itself, and it doesn't really make sense for me to teach you methods that are not consistent in the way that I'll mention. So consistency says the following: the discretized equations must formally become the governing equations as the grid size goes to 0. So this is a limiting process mathematically. As that delta x, delta y, as that goes to 0, the discrete form of the equations, in a finite difference context, we call those the finite difference equations, they must formally turn into the continuous differential equations that we started with. So this is a formal check on the numerical method. So if you think about truncation error, for example, truncation error is the difference between the discretized equations and the exact equations. That then must go to 0 as delta x goes to 0 for consistency. So let's take a simple example. Let's just take one first order derivative, du dx, and this is one form of an approximation. It's not the only form, but it's one that we'll commonly use. So it's ui plus 1 minus ui minus 1 over 2 delta x. Don't worry about where that came from. We'll see that in a later video. And this is the truncation error, the order delta x squared. That tells you how big the terms are that you truncated in order to get this approximation. So it's second order accurate. It's order delta x squared. The idea of consistency is as follows. As I formally take delta x going to 0, this must formally become this, the continuous derivative. Well, as delta x goes to 0 here, this term goes away. And as delta x goes to 0 here in the denominator, well, that's essentially the definition of the derivative. And so this will formally become that. All right, so consistency is a consistency check. It's inherent to the discretization method that we're using. And again, I'm not going to say a lot about it because all the methods I'm going to show you, actually except one, are consistent. But anyway, we need to emphasize how important that is. Another property that we need to check for is numerical stability. Now, this is one we will need to pay a lot of attention to for certain types of problems. Numerical stability says the following. Every time I enter a number into a computer, every time the computer generates a number from some calculation, there's a little bit of error. There's a round-off error. 2/3 is never 2/3. It's 0.666667 to the precision of the computer that's being used. So the question is, those small round-off errors that we know exist in our numerical approximate solution, what does my algorithm do with them? If they stay small, if they stay order delta x or delta x squared or whatever the truncation error is, if they stay of that same order, then the numerical algorithm is stable. If, on the other hand, those tiny little round-off errors grow and grow and grow and grow as I execute my numerical algorithm, then the method is unstable. So this is something that obviously is catastrophic. If our numerical method is unstable, we're going to get spurious results that have nothing to do with the reality that we're looking for. Because for an unstable method, the iterative process is going to diverge away from the exact solution, which obviously is the exact opposite of what we would like. Now, there's a closely associated property known as conditioning that we're going to look at in the next video. These are not the same. They sound similar because they're looking at what happens when I introduce small disturbances into my solution algorithm, but they're a little bit different. So conditioning quantifies the effect of disturbances in the system of equations itself, the linear system of algebraic equations. If I introduce a small disturbance, what is the effect of that? And that's regardless of the numerical method. It has nothing to do with the numerical method. It's a property of the system itself. Stability, on the other hand, determines the effect of the disturbances in the algorithm. So it's not a property of the system itself. It's a property of the algorithm that is iterating on that system. Another essential property is convergence. And this can get a little confusing because there's the convergence in the context that I'm going to describe right now, and then there's iterative convergence, which I've alluded to as well. So let me distinguish clearly between the two and describe convergence in the way that I mean here. So convergence here means that the numerical solution of the discretized equations approaches the exact solution of the governing equations as the grid size goes to 0. So this sounds kind of like consistency. It's different, but it's a formal check on the discretization, on the discretized form of the governing equations, the linear system of algebraic equations. Again, finite differences, finite elements, or whatever. So convergence is normally tested in the field, in practice, by checking for grid independence. So as you refine your grid, the error should come down, and it'll reach a plateau. And when it reaches that plateau, you say that the solution is grid independent. The solution I get really does not depend much on my choice of grid. When it's still coming down, it's still dependent on the grid. When it levels off, it's not. This is something we'll talk about more later as well. But that's the check for convergence, is as we refine the grid, as we reduce the delta x's and delta y's, as we increase the number of grid points, my solution should get better, more and more accurate, and it should converge towards the exact solution that we're looking for. The rate of convergence, so the rate at which it converges to that exact solution as I increase the number of grid points and decrease the delta x's, is related to the truncation error. So the higher the power, so if it's order delta x squared, that will converge faster than order delta x. Order delta x to the 4 will converge faster than order delta x squared, and so forth. And you can see the effect of this by checking the error. So for example, if you have an order delta x squared algorithm, then the error is of that order delta x squared. If I have the delta x squared, half squared is 1/4, the error will go down by a factor of 4. Whereas if it's order delta x, if it's only first order accurate, if I have the delta x, I will only have the error. So as you can see, the higher the power, the higher the order of the approximation, the faster the convergence, the rate at which the solution converges towards the exact solution. Now again, this is not the same as iterative convergence, and I'll always be careful to use the term convergence when I mean what I'm talking about right here, and I'll say iterative convergence when that's what I mean. This can be very confusing because obviously we're using the same terminology. The convergence in this sense is a property of step 2, whereas iterative convergence is a property of step 3. So remember, step 2 is the discretization step. Step 3 is the matrix solver step. So they're addressing two different aspects of the numerical solution procedure. Then finally, the last property I'll mention is what I'll simply call correctness, and I'll put it in quotes. This is something that's going to be problem dependent. Different fields will have different standards for checking the quote-unquote correctness of the solution. But the types of things that you'll look at are, you get your numerical solution, okay, the end of the numerical solution procedure, and you want to compare it. You want to see how well does it compare to any analytical solutions that you might have, to experimental results that might be available, and even other computational solutions that have been obtained using different methods, different codes, and you can compare yours against that. I always think of, and I talk about, a confidence meter. I always have 0 confidence to start, but actively doing steps to increase my confidence that my solution is correct by checking against available solutions of experimental results and so forth. Now there's 2 ways to formalize this. This is the 2 V's, validation and verification. These are terms that are used in computational fluid dynamics. They also have applications in other areas as well. Again, the point is to determine whether my solutions are accurate and reliable. How can I increase my confidence that my solutions are correct? So validation is a quantification of the modeling errors. So that's based on step 1. So that's asking questions like, am I solving the correct equations? Am I capturing the physics correctly? Is the solution qualitatively correct? Does it behave in the way that I expect? Validation is accomplished through comparison with highly accurate experiments. The only way to validate my results is to check against reality. The only way to get reality is to do experiments. Now, verification quantifies the discretization and iterative convergence errors. So in other words, from steps 2 and 3. See how this numerical solution procedure helps us in a number of ways to identify and mitigate the sources of errors and do this validation verification step. Okay, so verification is asking questions like, am I solving the equations correctly? Whereas remember, validation was, am I solving the correct equations? So here I'm assuming I have the correct equations. Now am I solving them correctly? Am I capturing the mathematics correctly? Is the solution quantitatively correct? Not just the correct qualitative behavior, but the correct quantitative behavior. Are the numbers correct? Verification is accomplished through comparison with benchmark solutions. So those could be exact or highly accurate numerical solutions that might be available from other sources. So again, you can see that the two V's together address all of the potential sources of error in the 3-step numerical solution procedure.